Good morning everyone, Dr. Nat here. So we are going to do lecture number 2. So lecture number 1 is going to happen tomorrow when I actually can do a live lecture. So we are going to learn about overview of an engineering drawing today. So I hope you are ready. So for today's content, we are going to cover graphics language, engineering drawing, projection methods, orthographic projection, drawing standards, as well as lettering. So what exactly is graphics language? Graphics language, well, we're going to do an exercise. So I have an object here, right? And I'm going to ask you to actually write down how you want to describe this object so that your friends can use your description of this object to redraw the object. Okay, for example, I'm going to try it myself. So number 1, I'm going to say this object it's almost like playing charade, right? This object has 3 holes. One hole is located on the side and 2 holes are located facing upwards. Okay, and then it is symmetrical. So as you can see, what I'm writing down is describing the object, but it doesn't help me to completely describe it. For example, I can't actually tell you I have this curve, that this object has a curve like that. It's pretty hard to do it. And we couldn't actually describe this extruding or protruding feature of the hole. So the language, yes, it helps to describe an object, but it doesn't help us to completely describe all the features. To some extent, it can do it, but some features cannot be described well using word language. So you can easily understand that the word language are inadequate for describing the size, shape, and features completely as well as concisely. Now, graphic language in engineering application use lines to represent surfaces, edges, and contours of objects. You have seen it in the example just now. Lines are used to describe contours, edges, right? Lines are used to describe contours, edges, contours is this guy, surfaces, edges, and contours. So this language is known as drawing or drafting. A drawing can be done using freehand instruments or computer methods. So freehand is just sketching. Instrument is using the protractor and jangka lukis, I don't know in English. Protractor, where you can protractor rulers, and for computer methods you use AutoCAD or SolidWorks. So this is an example of freehand drawing. Here you can see that freehand drawing does not use anything aside from pencil and an eraser. The lines are not crisp, the lines are not neat, but it describes the features well. And then we have instrument drawing. Here you can see that the drawing is more precise. It tells us the dimensions and which side the dimension refers to, indicated by the arrows. Here, from this diagram alone, I can already tell that this hole, these 3 holes times 3 holes, has a diameter of 5. So this is called a diameter. And here, this drawing tells me that I have a contour of radius 9.5. So see how they're using both graphic as well as word. So this is the graphic part, and this is the word language to describe what is going on for this diagram or for this object. Now this is from the top view. No, sorry, this is from the top view, yes. And this is from sideways. So from the sideways, we can tell that from here, from the center of the hole to this part, it is 11.1. So you can draw it precisely, or you can remodel it using a 3D printer, or you can redo it in AutoCAD software, where you can reproduce this accurately and precisely. So here what we got from this slide is that diameter is indicated by this symbol and R is radius. Now computer drawings are usually made by a commercial software. For this class we are going to use AutoCAD. My previous students have told me that once they have learned AutoCAD and be familiar and very hands-on with AutoCAD, they are able to transfer their skills into SolidWorks. And they told me that they have managed to use SolidWorks easily because of the foundation that they have learned from this class. So don't worry, if you want to learn SolidWorks later, it is totally possible. What you need to know is the foundations of engineering drawing first. So, elements of engineering drawing is composed of two things. The first one is the graphics language, and the second one is word language. We have seen this just now, where the lines describe the contours or the holes or the edges, and we have word language describing the dimension as well as the diameter as well as the radius. The word language can also be used to describe the location and the specification of the object. For example, I want the audience to know that this model A is used for equipment B, for example. So without this information, the readers would not know that model A is for equipment B. They will only know this is model A, right? They wouldn't know that it is supposed to be used with equipment B. So how do you make sure that the readers know this information? You write it down in your engineering drawing. So for example, you want to communicate with me about your drawing, that this drawing is made for etc. etc. So you tell that in the engineering drawing itself. You don't have to WhatsApp me. You have to just write it down in your engineering drawing. The notes need to be concise and only for the engine and caters to the drawing itself. It doesn't, you should not put like, please give me more marks or stuff like that. It should only be relatable to the drawing itself. Okay, so basic knowledge that you need for drafting is graphics language, which we will cover in this class for the entire semester, and also word language. Under graphics language, we will learn about line types, projection method, and geometric construction. So, what is projection method? Projection method, there are two types. The first one is perspective, and the second one is parallel. So we will learn about both, but for this class, we will focus mostly on parallel, orthographic, and multi-view. But you will have to know how to do this one as well, oblique and axonometric. So the projection theory is used to graphically represent 3D objects on 2D media. 3D on 2D media. So we live in a 3D world and we want to translate it into 2D so that we can recreate it in 3D again. So the projection theory is based on two variables, which is the line of sight and plane of projection. So what is plane of projection and what is line of sight? So line of sight is an imaginary ray of light between an observer's eye and an object. So this is your eyes, right? Looking a little bit crazy here, and the line of sight is from the edges of the object. That gives your eyes the information of the shape and the contour of the object. Now for parallel projection, you can see that the line of sight is straight. But in perspective, the line of sight actually converges into a point. It converges into a point. Now, again, parallel projection, the line of sight, LOS, is parallel or actually straight. It does not converge. And for perspective projection, the line of sight converges into a single dot. Now, the ones that we will use for AutoCAD is parallel projection, because perspective projection does not give us accurate dimensions. It gives us a distorted image. Now let us see how that works. So we talked about line of sight. We have line of sight for parallel as well as line of sight for perspective projection. Now we're going to talk about plane of projection. The plane of projection is an imaginary flat plane which the image is created. So we have our line of sight, LOS, here, right? And then we imagine a paper passing through the line of sight. And we will draw the object based on where the line of sight appears, and we will recreate the diagram. So here you can see that the object is not distorted. It maintains the original features of the object that we want to draw. Meanwhile, for perspective projection, you can see that the features are maintained to some extent, but when we are drawing it at this point, when you put a plane over here, what you're going to get is just a dot, right? Because perspective projection does not maintain the features. But you're going to ask me, hey doctor, but here the features are still correct, but they are smaller. Wouldn't that count as not distorted? Now this is a representation of a 3D object in 2D perspective. It's not obvious that the perspective projection is problematic here, but I'm going to show you how problematic it is in the 3D world. Right, so so here, this is your line of sight. You are standing here. Just going to draw a stick figure here, indicating that's where you are. And when you view the road from a perspective projection, what you're going to see is the road is triangular. But because our brains are smart, we know that this is actually not the case. When you move forward, when you walk along the road, you can actually see, oh, the road is actually like this. It's straight. It's actually rectangular. Right? This is the actual shape. But in perspective projection, what you see is triangular shape of the road. And this is the same case for other objects, such as KLCC, right? We have seen KLCC. We know it looks like this parallelly, but if you're viewing it from down here, what you see is KLCC looking like that from down. But you know that KLCC is like this. So this is the disadvantage of perspective projection, because the line of sight is not parallel to the object. You won't be able to capture all the features accurately, whereas parallel line of sight gives you accurate representation of the object. However, it's not possible to view KLCC parallelly because KLCC is way too huge. So we would need to be situated very, very far to actually view KLCC parallelly. If you are very near to KLCC, what you're going to get is perspective projection. Because why? Let's try to imagine this again. Okay, let's try to draw KLCC. So this is KLCC, right? Okay, I'm sorry for the very bad drawing. So parallelly, if you want to view this parallelly based on the line of sight, right? What you need to do is you need to be very, very far for your eyes to view this parallelly. But if your line of sight, if you are situated under KLCC, where is your line of sight? It's here, right? This is your line of sight. So your line of sight is here. So what you're going to see is a distorted image of KLCC, which looks like that. Okay, you can try it. Go to KLCC, stand under KLCC, you will see a distorted image, and then you can view KLCC from UPM. Maybe you can see it, maybe you can't. You will see the actual shape of KLCC is actually like a tower. Okay, moving on to orthographic projection. So what we have covered so far is projection theory. We have two types of projection theory. We have perspective and we have parallel. And what makes perspective distorted compared to parallel is the line of sight converges to a single point. And parallel, the line of sight does not converge. And therefore, perspective does not maintain the features of the object when we draw it on the plane of projection, whereas parallel maintains the features accurately. Okay, moving on to orthographic projection. So orthographic projection is a parallel projection that we have learned just now, in which the parallel lines of sight are perpendicular to the projection plane. We have seen this, we know this, and then but for orthographic projection, we can actually view it from many angles, from the top, from the side, from down under, from here. So it depends on where you want to view it from. So this is giving us the same object, but we are viewing it from the top. Therefore, what we're going to get is this this rectangle. And from this side, we're only going to see up until this point. So you see, not until this point. You're going to see a distorted part of this because this is angled. So you are going to see only this part, only that size. So we will discover more about this. So from here, what you need to know is orthographic projection is a parallel projection technique in which the line of sights are perpendicular to the projection plane. So you have two projection plane here. Number one is here from the side and another is from the top, right? So orthographic view depends on the relative position of the object to the line of sight. So for a 3D object, this is a 3D object. If we only view it from this side, we will get a 2D representation of a 3D object. And obviously, it does not tell us whether this side has holes or whether that side has contours. It only tells us about the feature over here. So to represent a 3D object accurately through 2D drawing, we need to have more than one drawing. We need to have more than one orthographic view of the object. Okay, I'm going to write that down. We need to, for a 3D object, we need to have more than one view to accurately know how it looks like. Okay, a 3D object represented in drawing in 2D form needs to have more than one view for us to actually know how it actually looks like. If we only have one view, which is this guy over here, we can't really tell what happens over here or over there. And because we need more than one view, this is called multi-view drawing. Multi-view drawing of orthographic view. Orthographic view is a parallel representation of the object from that view. We can have multiple views, and this is called multi-view drawing. Now, orthographic view can also be used to draw objects that are rotated and as well as tilted. So for orthographic view that requires more than one drawing, this is called multi-view drawing. But if we rotate it, sometimes we don't need more than one view. It is sufficient to describe all of the features of the 3D object. Now, if the object is tilted and we draw the 3D orthographic view of this, we can actually get a 3D view if it is tilted. Now, this is called axonometric drawing. To summarize, what we have learned so far is multi-view and axonometric. Okay, and this is under parallel projection, where we talked about orthographic. What is orthographic? Orthographic view depends on relative position of the object to the line of sight. We have our plane of projection. We connect it with the line of sight. It depends on whether it's just, if it's rotated or tilted, you draw whatever that the line of sight tells you. From parallel projection, we have the orthographic view. An orthographic view sometimes can be drawn in multi-view, 2D drawing in multiple views, and axonometric is 3D when tilted, when the object is tilted. Okay, again, axonometric, this is 3D, 1, 2, 3, 3 dimension. But for 2D, we only have a surface level, or like it doesn't tell us well, I think you're going to get what 2D and 3D is throughout the class later. Okay, so this is an axonometric drawing. It gives us more than one view, right? It gives us the top, the side, the front. This is axonometric. The advantages of axonometric is that it is easy to understand, right? You can tell what this object looks like because this is what we see in the real world as well. The disadvantage is that the shape and angle distortion. The right angle becomes an obtuse angle. Right angle is 90 degrees. But if we were to measure this, we know that this is not going to give us 90 degrees. 90 degrees is like this. This is not 90 degrees. Okay, what's next? And then an example is distortions of shape and size in isometric drawing. So one of the distortion that's really obvious is that this guy, which is a perfect circle, in this axonometric drawing looks like an ellipse. So axonometric is easy to understand, but it doesn't give us accurate dimensions of the object. And if we were to redraw this, it's kind of hard, because a circle is now an ellipse, a right angle is now more than 90 degrees, and so on. This is multi-view drawing. Just now was axonometric. We had a 3D view of the object. For multi-view drawing, we get only 2D view of the object, and that is why we need more than one view to represent the 3D object. So this is the first view, and this is the second view. Now the advantage is that it represents accurate shape and size. You can see that the whole is a perfect circle. The square is a square. The right angle is a right angle. This disadvantage is, however, it requires practice to write it as well as to read it. It's not straightforward. You have to really use your imagination to figure out how this would look like in the 3D world. Now let's talk about drawing standards. So drawing standards are a set of rules that govern how technical drawings are represented. So let's say drawing standards are used so that drawings convey the same information or same meaning to everyone who reads them. So for us, we actually use ISO, International Standards Organization. For other countries, they use their own standards. We also have the Malaysian standard, but mostly we use ISO, International Standards Organization. So Japan is called JIS, USA is called ANSI, ANSI, UK is called BS, Australia is called AS, Turkey is TS, and so on. What is relevant to this class is going to be MS as well as ISO, but the ones that we will use for our software is ISO later on. So for Japan standards, they have codes to represent what is what. So for example, GIS standards Z8311 tells us the size and format of drawings. So if you Google that, you will find out what are the standards for sizes and format of drawings. And Z8312 tells you the standards for line conventions under the Japanese standards and so on. Japan standards. And then this is the drawing sheet. We have A4, and A3 is twice of that for A4, A2 is twice of that of A3, A1 is twice of that of A2, and A0 is twice of that of A1. So what we're going to use for this class is A4 and A3 drawing sheets on AutoCAD. So these are the measurements in millimeters. So this is how a drawing sheet looks like. We use Type X for this class, which is in landscape. Type X has a margin called C. The margin size for A4 and A3 is 10, whereas the margin size for this side, where the binding happens, is 25 millimeters. So you will do this on AutoCAD before you can start drawing your object. So again, you will need to construct these border lines or margins, and here is called the title block. The title block tells your name, your metric ID, the department, the UPM logo, and so on. So it's basically your identification. So again, we will only use Type X in landscape. This is the measurements for the borders. We will do this in AutoCAD later. Okay, so we talked about standard codes, we talked about drawing sheet sizes, and we also talked about drawing sheet measurements. So now we're going to talk about drawing scales. So this is the size in drawing. So size in drawing is obviously sometimes smaller or sometimes bigger than the actual size. To represent this, to show that the size in drawing is smaller compared to the actual size, you can write it in this convention. So let's say the size in drawing is 10 millimeters, but the actual size is 20 millimeters for this side. What you're going to write is 10, 20, and you're going to make this smaller. So it's going to be a scale of 1 to 2, whereby 1 tells you the scale of the size in drawing, and on the right side tells you the scale of the actual size. So if the size in drawing is 10 millimeters, the actual size is 20 millimeters, and so on. So if this guy, and based on this scale, I can actually figure out the actual size. So if this is 5 millimeters, the actual size I know for sure is going to be 2 times the size in drawing. So this is going to be 10 millimeters. So this is the function of scale. So scale 1 to 1 tells us that what we're drawing is actually the full size in real world. Scale of x to 1 tells us that the drawing is bigger than the real. So this side is real and this side is drawing. So 1 is obviously the smallest number to write down scale. 1 is the smallest number to write down scale. This is drawing. You always start with drawing. 1 is the smallest number. Do not use decimal points. Let's say you have a scale of 10 to 1. So you know that the drawing is much bigger than the actual size. So if the drawing is 10 millimeter, the actual size is actually just 1 millimeter. And a scale of 1 to x tells us that the drawing is reduced in size. So 1 millimeter in drawing, so if this is 1 to 10, 1 millimeter in drawing is 10 millimeters in actual size. So this is how drawing scales are used. Again, this side is always drawing, left side. This side is always the real object. 1 is the smallest scale. So if 1 is on the left side, the drawing is smaller. If 1 is on the right side, the actual size is smaller. Dimension numbers shown in the drawing correspond to true size of the object, and they are independent of the scale used in creating that drawing. What does that mean? So let's say I have an object. Okay, this is my object. So this object, if I use a ruler to actually identify what the dimension is, it is 5 millimeters. But the scale on the object, the dimension on the object drawn, okay, let me rephrase that. Okay, delete. So let's say I have an object, right? Let me just draw this rectangle. So I use a ruler, and the ruler tells me that this is 5 millimeters. But the dimensions that I put on this drawing, I put it as 10 millimeters. Okay, let me try to say that again. I measure the drawing using a ruler and it tells me 5 millimeter. But the dimension that I put in this drawing is 10 millimeter. What does that tell you? It tells you that the dimension of the drawing is 5 millimeter, the actual size is 10 millimeter. Therefore, the drawing is drawn 1:2 scale. The drawing is drawn 1:2 scale. Both of this information is provided in the drawing. Measuring the drawing itself tells us the scale on the left. The dimension used, the dimension that is put into the engineering drawing tells us 10 millimeter. Even though when we measure it, it's not 10 millimeter, but the dimension written there is 10 millimeter. That tells you the actual size. And because we know the actual size as well as the size drawn, we know the scale of this drawing. It is 1:2. This is what it means when the true size of the object are independent of the scale used in creating that drawing. The dimension tells us true size. The dimension tells us true size. And then we move on to basic line types. So if we have a continuous thick line, this is called visible. If we have a continuous thin line, this is used for dimension, extension, and leader line. And then we have a dash thick line. This is called a hidden line. And a chain thin line is called a center line. So these are the lines that we will be using a lot in AutoCAD. These are the lines that you need to know. You need to understand how it works for you to read an engineering drawing. So visible lines represent features that can be seen in the current view. Hidden lines are features that cannot be seen in current view. Center lines are representing symmetry, path of motion, center of circle, axis of symmetrical parts. And then dimension indicates size and location. So let's take a look of these lines. Okay, so we have an example here. So here I have a continuous thick line. Continuous thick line. What does this tell us? A continuous thick line gives us information that this is what is visible when we look at it. And then we have a thin line. Continuous thin line is used to indicate our dimension. So if you can see that this line is slightly thinner. This line is slightly thinner than the visible line or the continuous thick line. And then for the extension line, we use, extension line. We also use a continuous thin line. So extension line, this is the extension line. The extension line gives us a guide for the dimension. We put the extension line first and then we put the dimension line. Extension line and then dimension line. And then a leader line gives us information, for example, the radius. So a leader line also uses a thin line. And then finally we have our center line. The center line, you can see that it is almost like a dash. So center line is like this. It's called a chain thin line. Chain thin line. So a chain thin line is used to indicate the center of the whole, also to indicate symmetry. So text on engineering drawing is used to communicate non-graphic information as a substitute for graphic information. Thus, text on drawing must be used with a certain size, a certain thickness in our software later. So this is an example of an engineering drawing with placement text. So this is your title block. The title block tells you the identification of who drew this engineering drawing, when was it done, what is the scale, who drew it, which company did it, and then if there's any other information needed, you will also put it in the title block. And these are notes. I have mentioned to you this before. Notes are used to communicate things that cannot be used, that cannot be represented graphically. And then we have dimensions and notes. This is extension line. We also have dimension line here. And then we have, do we have a center line? We do, but it's not very visible here. And then these are other things that we have not covered yet. Don't worry, there's a lot of information, but we will also use it hands-on, so it will be more easy to remember later on. Okay. Lettering standard. For this textbook, they said they are using ANSI standard, which is US standard. For ANSI standard, they use a Gothic text style, either inclined or vertical. Use all capital letters. Use 3 mm for most text height. Space between lines of text is at least 1/3. So the way that you're going to do this in AutoCAD is just clicking it on settings. Typically, we will use ANSI or ISO for lettering, but the rest is ISO. So this course only use vertical. Use both capital and lowercase. For the height, we will use 3 mm. Sometimes it is not visible, so we will use between 4 to 8 text in height. And then space between lines, we will follow ANSI rules, which is 1/3 text height will be the space. So icebreaking, we'll do this tomorrow. And that is all for today's lecture. So I will see you tomorrow on Thursday. Take care, everyone. Make sure to understand the content of this lecture. The slides can be found on Putra Blast. You may download that and make your own notes. Okay? Bye-bye. Take care.